without further ado, I think I'll hand over to Jonathan Churchill from RAL. Jonathan's been at the Rutherford Appleton Laboratory since 2006, where he's been working on a variety of high-performance computing systems and services before he moved over to take on JASMIN, the UK's environmental data analysis platform. He's guided it through its growth from its initial stages, and this evening has agreed to talk about the range of science that's performed on the platform and to lift a little bit of the lid on its architecture. So over to Jonathan.
Great, thank you very much. So about 8 years ago, my boss came, almost to the day, my boss came to me and said, what would it take to run a big petabyte storage platform? And at the time I was running a small storage platform that was a couple hundred terabytes, had a lovely interface, and I went, yeah, that can't be that hard. So he went away, and then he came back again and he said, oh, by the way, this group, they think they need some bit of virtualization as well. Can you do that as well? And I went, yeah, that's okay, yeah, we've done one of those. And then he came back another couple of weeks. He said, well, actually, what they really want is a cloud. Could you do one of those as well? And I went, well, that's a bit harder because nobody else has really done clouds in the UK at that time with any kind of scale. We'll talk about a little bit of that in the talk. And then finally he came back a week later and he said, well, actually, what I really think they need is a batch computer, but they don't really know that yet. So can you do one of those as well? And so this was November. This was like October 2011. We went from that to a £5.5 million procurement, public sector, which is, I don't know if anybody's in the room ever tried to do that. It's really hard. And we went through that with the target of actually the government gave us the money and they gave us a target of getting up and running by March of 2012 and doing some science. So we went from zero with nothing in the machine room to public sector procurement, which usually takes months or years, to having an operational platform in the middle of March 2012. So from that basis onwards, we kind of took off a little bit. And what I'm going to talk about today is the platform which has eventually become JASMIN, supporting thousands of users, mostly in the UK, but around Europe and elsewhere as well, for doing environmental science. But first, I'd like to dispel a little misconception, well, actually two misconceptions. One is, on the title of the talk, it says a supercomputer. As I'll talk about in this talk, JASMIN is what we call a super data computer. We invented the term, and as you'll see, that's because JASMIN is data-heavy, compute-light, whereas most supercomputers are compute-heavy, so they might have hundreds of thousands or millions of cores, but relatively small amounts of storage to go with them. So JASMIN is the opposite way around, and we'll talk about why that's important. The second thing I want to dispel is a misconception, is a BCS problem. I don't know if anybody's read IT Now. Does anybody read IT Now, the magazine, the BCS one? So I think it was in the last issue, there was an article about Dirac. And they were talking about how Dirac compared to other tier 2s, one of which included JASMIN. And JASMIN was badged as being hosted at the Hartree Centre, which is up at Daresbury. It is definitely not. It's centred at the Rutherford Appleton Laboratory down here. And I can tell you that because this is where it sits physically. Does anybody, if everybody's aware of the Rutherford Labs, this round thing here is diamond light. You can see a few RAL's faces in the audience here. This is ISIS, well, actually not that itself, but those are the detectors. That's the neutron source. Buried in here somewhere is the central laser facility, which holds multi-petawatt pulse lasers. And then here is R89, the data centre where JASMIN sits. And over the road is the old Atlas data centre, which I believe one or two in the audience might actually have used the computers in there a long time ago. But it's been refurbished, and we're about to go across the road here to put JASMIN both in this data centre and the one across the road. And there's a whole talk that goes with what we've managed to do in order to connect the two data centres together, but not something I'm going to talk about today. So, what is environmental data analysis? Here we have two examples of data from earthquakes. The top left-hand corner, so this one here, is taken from the Wellington, New Zealand earthquake, which was a few years ago now. You can see there's a 10 metre movement of ground, which is enormous. It was a really big earthquake. And the team of scientists who generated this image, which actually comes from the last big earthquake in Italy, also a few years ago, they're able to generate this kind of data from with a satellite from space at centimetre resolution, not metre resolution, in near real time. So for the New Zealand earthquake, they were able to tell the New Zealand government at a time when their communications were mostly down where the worst case place of the earthquake was, so that they could get the rescue services to that, rather than worrying about what the stuff that they could actually see around them. This picture here is actually taken with data from that satellite. It's actually a radar mission. I'll talk about a little bit about that later. And it's a composite between where the ground was before the earthquake and where the ground was after the earthquake. And you get these things which sort of look like a bit like stress relief patterns. But if you imagine if all you're doing is just measuring data that way, it doesn't really tell you where the worst case problems are on the ground. If anybody's seen, there was a film about Etna on the BBC not that long ago. I don't know if anybody saw that, and they were talking about all the sensors that they actually placed on the Etna volcano in Sicily, and they've got GPS sensors, and they use that to see when the volcano is starting to rise up. Well, these guys can actually do it without sensors on every earthquake and every volcano on the planet in near real time, without all of those sensors. So this is groundbreaking stuff. So that's earthquakes and volcanoes. It's effectively Earth observation. This picture down here is a snapshot of a movie of the climate, a simulated version of the climate over 10 years at high resolution. So it includes all the seas, all the clouds, all the ground, as you can see. And this is the climate science community. This is done in support of the work that goes on worldwide for the IPCC Climate Change Report, so the Intergovernmental Panel on Climate Change. JASMIN holds about 40 or 50% of the data that went into the last round and is committed to holding 60 or 70% of the data in the next round. Now, when I tell you that the first round was about 2 petabytes of data, so petabyte is 1,000 terabytes, which is 1 million gigabytes. So that's 2 petabytes is 2 million gigabytes of data. And the next round is 10 times that for the accuracy, which I'll talk about. So there's a big community of scientists doing that kind of thing. But then we have this other sort of stuff. Now, when I heard about this work, I was completely blown away about it. Every year we have a user conference, and this guy came up. He works at CEH up at Wallingford, and you may have seen, I think was it last summer, there was a call for you to go out into your gardens and see which butterflies you could find. And then there's usually an annual call for people to go out and find out which birds are in their back gardens. So all of that observational data goes into a big database. But as the scientists pointed out with this one, most people tend to go out when it's daytime. Usually they don't go out in the rain. They go out when it's lovely and sunny, and there's different kinds of people who go out. This is a group of walkers here, and they're out in the countryside rather than in their back gardens. So there's massive amounts of bias that goes into this data. So, for example, these guys are never going to see a barn owl because they come out at night. It's a very simple observation. And what they do in order to produce accurate reports from that is they remove all the biases by running a bunch of Monte Carlo simulations between the analysis data which you give them and the analysis data which the professional scientists actually take. And this amount of computing is massive. And I'll talk about that in a second. And then there's a bunch of other people there's about 80 different projects on JASMIN doing a huge range of things. I'll talk a little bit more about some of these, but we've got people who do biogenomics, so that's the study of bugs in the environment. So it's not just the traditional things. We've got people who are analysing the data from the satellites that are going over the Arctic and the Antarctic, so that's looking at things like the ozone holes, where the ice flows are going, all of that kind of stuff. And these are research virtual environments that they built on top of JASMIN, looking at the data and exposing it either out to the public or to the rest of their user community. And this stuff has very high-profile results. From that little picture of people grabbing butterfly and bird data, came the UK Biodiversity Indicators report, which is a government report, and it's all based on work that happened in JASMIN. I did read the report, and unfortunately they didn't bother to actually credit JASMIN, but you can't have everything. I'll show you an example in a second where they did actually credit it. So the earthquakes and volcanoes people have a ton of stories on the BBC website because it's obviously very important, and it's quite critical what they're doing. These guys are an interesting example of where they've used a bunch of facilities on JASMIN to build their infrastructure, and that's fairly common with JASMIN, where it's not just about computing, it's about databases, it's about websites and how they can build those things up. We also have this really nice story from called Prize. So this is a project which the International Development Agency have been running in government, or have been funding, and it uses data on JASMIN, and is an interesting example of where different data sets get used. So these guys are taking satellite data for sub-Saharan Africa, finding where the pest insects are, so things like plagues of locusts, detecting where they are on the ground, merging that data with weather forecasting models and being able to predict where the locusts are going to go next. And then what they've built is a system where the farmers in the field can, with their mobile phones, can actually subscribe to alerts about for different pest insects, where they're actually going to go next. I'm not quite sure what you do with the data if you get a plague of locusts, but maybe you spray your crops or something. But anyway, so that was quite interesting. We actually had Parv Ghosh came to the RAL, and if you actually read this story on the BBC website, hopefully the picture is still there of the big blue picture I had on the slide at the beginning of this talk, and JASMIN actually gets credited, which is highly unusual for computer systems. Usually it's just, there's some IT in the background. So it has high profile, but why do we need a huge computer to actually do this? Well, before JASMIN first started, people used to do most of their analysis on the desktop. So they either had a laptop, or at most they had a couple of server computers, and that was probably okay before JASMIN started. But at the time JASMIN started in 2011-12, it was becoming clear that you couldn't do that any longer. So as an example, this comes from the Upscale project, which in around about this time, 2011-12, had the complete machine, supercomputer run. These are the guys who generated that climate picture I showed you earlier. They had the whole of the Hermit supercomputer in Germany for a week. Usually when you get time on a supercomputer, it's a few hours and you might get like a third or a tenth of the available cores. That's a massive grant of time. And what they were doing was effectively running the weather forecasting model at tighter resolution than the Met Office actually does their usual forecasts at. So at the time, the Met Office were doing their forecasts at about 25 kilometre resolution. So this is Europe at 25 kilometre resolution. And you can see if you back off on the resolution here, this is how the weather forecasting models used to be run. They used to be so bad at one point that Britain was joined to France and there was no island. So clearly that's not going to give you... And the Himalayas, not the Himalayas, the Alps really don't exist at all. So this isn't too bad, but it's, there's bits of this stuff that's missing. It looks like Italy and, Sicily are kind of joined together and it's all a bit blocky. So they run it at 10 kilometre resolution, but it took the whole of the machine, the whole of the week to generate. So clearly that's not good for weather forecasting, and so that's why we have to back off with the forecasting. But this one run generated nearly 1 petabyte of data just from one simulation run. and then they had to analyse it. And the supercomputer didn't have enough storage to keep the data, so the only place to bring it was back to JASMIN so that we could do the data analysis on a separate system. So this is an example of the kind of scale that we're talking about. One simulation run generates 1 petabyte of data, whereas in the past, these kind of things, you know, a few gig or at most a terabyte of data. When you think that, you know, my memory stick is 64 gig of data, you can put it on here. You can't get a petabyte of data. Well, not yet, you can't. So at some point you will. And other examples of the kind of scale. Again, related to climate, there's a huge worldwide climate research program going on. This is an international collaboration of which JASMIN is part, sharing data from different models which go into the IPCC climate change report. So part of the problem with climate analysis is nobody really knows what you need in order to do a model, because we can't look into the future, we have to guess at what's going on. So everybody's got their own guess, and that effectively means a different model. And those models all have a bunch of different parameters, and nobody really knows which parameters actually make any differences. So the IPCC climate change report actually is the best view of what most of the models actually predict. There are some outliers from that. But in order to do that, you have to do the equivalent of what these kind of guys were doing at high resolution to find out which of the things actually matter. So you're not talking about one run now, you're talking about, you know, there's, whatever it is, 200 or something different projects going on here. So this data is shared between climate research programs across the world. JASMIN is one of those. And that means that we're exchanging data. But in order to do these models, we're not just saying, well, you guys over there, you can do one model and we'll do this other one, and then we'll get together at a big conference and talk about it. You actually need to be able to compare the results from the different models. And that's what one of JASMIN's purposes is to have all of the data in one place to be able to intercompare the model results. When I tell you that 1 petabyte of data that I'm talking about, if at best, if you think your broadband connection has got even the best ones at a gigabit a second, and I don't think there's many people in the room, I certainly don't have that kind of thing, we're probably an order of magnitude away. Even if you've got 100 gigabits, so 100 times that, it takes a day to move a petabyte of data effectively across the internet, and that's really, really hard. Somebody actually, one of the US groups did it, and they didn't quite make it, and some of the data got corrupted when they did it. And that was 2 or 3 years ago now, and nobody's really managed to better that. The whole of the network connection to the Rutherford Labs is 100 gigabit. So we could swamp it by moving a petabyte of data. And clearly there's a load of other research that's going on as well. So moving petabytes of data around the world is just not feasible. And that means you want to do your intercomparison in the same location. So there's this concept of data gravity, which means that you can't really move the data around. You need to bring the compute to the data. And another example of the kind of scale that we're talking about is the European Space Agency's Copernicus missions. Eventually there will be 11 satellites in space. JASMIN is the UK's data hub for that data. So we provide all of the data for UK researchers and commercial data users as well from one central location. These satellites, eventually there will be 11, they're not all up in space yet. They're generating about 10 terabytes of data a day from space. Actually, it's quite a cool project about the way to get the data down, but again, that's not for this talk. So that's they're talking about 6 petabytes a year here. Even at 10 terabytes a day, it's at least 2 petabytes a year, and we're committed to hold everything and make it available for the 20-year lifetime of all of those satellites. So that's, if you think it's 6, that's 6 times 20, that's 100 petabytes of data. And the data, as I talked about with the observational bias thing, with the prize project, different pieces of data will overlap. So there's again another driver for actually putting all the data in one place. So you've got the Earth system models here, you've got hydrology, so that's water flow, that comes into climate models as well, and that flows into the models, but you actually go and measure this in real life. People doing forestry use Earth observation to find out what the size of the canopies are in the forests. And there are loads of projects going on in JASMIN, which are all, and you can see they're all interrelated with one another. So actually having, if I'm a researcher and I'm in an organisation, I've got my data set, I've just been out into the environment, and I've measured a bunch of data to do, I don't know, like rainfall in the Amazon or something. I've got my data set, and I want to pull in all these other data sets. I'm not going to have the storage at my location to be able to suck in a couple of petabytes of climate data or Earth observation data to compare my data sets to. And also it's going to make it very hard for me to share it with all of my collaborators in the UK and Europe wide, because they've all got to have logins and get access to the data. So these were the drivers for doing JASMIN. And JASMIN was considered to be the missing piece between all of these systems back in 2011-12, or at least this was the concept that we tried to get going and hopefully have been successful in doing. So we always had these things which you could measure data. I'll talk about a little bit more about this aircraft in a second. This is owned by NERC and is an example of... so NERC funds JASMIN, Natural Environment Research Council, and they also fund a bunch of other things as well. So they've got the aircraft, if you know the Boaty McBoatface boat, the Sir David Attenborough. That is something else that's paid for by NERC, as is the base in the Antarctica, the British Antarctic Survey, and all of those things are data generators. And then we have the simulation engine. So we have direct links to the Met Office supercomputers, and when they're not doing weather forecasts, they're doing climate research. And so all of that data comes out of the Met Office, comes up some pipelines, disappears into JASMIN, as does data from, this is the academic supercomputer, which is hosted up at Edinburgh, partly funded by NERC as well. So we've got all of these pieces together, but we never had a single place to do the data analysis and to compare all those results together. And that's what was driving JASMIN. So in this talk, I'll talk a little bit about the data sets that are available on JASMIN and the CEDA archive. So CEDA is the Centre for Environmental Data Analysis. I'll talk a little bit about what that actually means. What happens when you log in as a user into JASMIN and how that's different from a supercomputer. How we use the private clouds, and that's quite an interesting story as well. JASMIN was a kind of leader in this field. We also have a batch computing part, which we call Lotus, which is actually very much more a traditional supercomputer. And to tie all of that together, we have what I think is quite a cool network, which is quite unusual for HPC centres. I was at a conference last September, and basically there was people from all of the HPC centres around the world, and nobody had a network like this for their supercomputer. And then, if we've got time, I'll talk a little bit about high-performance object stores, which I think is quite cool and is actually is lighting up the object store market as well. So, a big chunk of the data that's on JASMIN is managed by CEDA. CEDA is an organisation in which about half of the scientists, they're all based at RAL, or most of them are based at RAL. About half of them are curating data. So what that means is they're taking data sets, creating metadata for them, so when the image was taken, what the parameters were on the instrument at the time that the data was taken, and keeping those models up to date. The archive is about 13 petabytes right now. This was from about 3 months ago, and it creeps up all the time. It's a mix of these data sets I've talked about, real measurements as well as simulated things. 200 million files. To give you a comparison, the whole of JASMIN is about 900 million files for all of the storage. Sam Pepler, who is the archive manager, claims that there are 55,000 registered users, but then when I asked him the same question 6 months ago, he told me there were 12,000, so I don't know what you believe. Now, you can see the number of users here, and there's been a general creep for the last 20 years since CEDA started, and that's obviously more to do with the amount of data that's coming out and is being available. Fairly linear. This spike here is all the climate researchers, and obviously that's a very hot topic. We've seen all the stuff that's been going on in London in the last few days. So that's the archive. Some examples of those datas. I mentioned the FAM aircraft on the earlier slide. This is the aircraft that, if you remember the volcano with the unpronounceable name back in 2010, if you remember back that far, there was an aircraft that went up to find out what the particle density was. This is the aircraft that went and did those measurements. All of that data is on JASMIN, along with a bunch of other data. That's not the only things that they measure. There is, as you can see here, methane, particles in the atmosphere, and it flies all over the world. So they've been down to Lagos, over to India, over in the Pacific as well. And the climate science people, which I've just mentioned. I mentioned the petabyte of data they're doing for the current climate science program, and they're now gearing up for 10 times that amount of data or more for the second round of data going into the next IPCC report. And then finally, the Sentinel data, which I've also mentioned. Or the other thing I didn't mention on the picture of RAL, across the road from us is the Space Catapult Centre. So if you've seen in the news, there are all kinds of catapult centres which the UK government funds. One of them is a space catapult. So over the road from us are a bunch of little startup companies who are either using data from space, or some of them are actually trying to launch satellites. We also have the European Space Agency's headquarters on the same site. And so we have a direct 10 gigabit link from JASMIN across the road into this, and this is all the commercial data users. So there's a ton of lists, if anybody's particularly interested in this, they're probably not. But interestingly, you get things like land cover, soil moisture, ozone, ice sheets. Lots of these data sets are derived data sets. So you take raw data from satellites or wherever, or you've measured them in the ground, and then you combine them with other data sets to form new data sets which people can then use further on. And you're pushing all of that data into the archive. So it's this virtuous circle of more data coming in from the environment, getting processed on JASMIN, going back into the archive so it can be available for other researchers to do more science more accurately with more data. So how do we actually do that? So I'm going to talk a little bit now about under the hood. This is kind of, you can probably tell from the last few minutes of me talking, is that I'm not a climate scientist. I'm a systems person. So my job is to actually build the super data computer, architect it, and spend your and my taxpayers' money, of which we've spent £24 million to date on this thing. And we have a rolling programme of upgrades, which is about 2 or 3 million a year to keep this rolling. So, as I mentioned, it's a super data computer, and what that means is that we're focused on storage more than data. We currently have disk capacity of about 44 petabytes of disk storage, and with a performance of about 500 gigabytes a second, which is difficult if you've never really kind of measured this before. But if I tell you that puts JASMIN in the top 10 in the world for I/O performance, unfortunately, because JASMIN is a super data computer, we can't measure it with the same benchmarks that people do on the benchmark. So we don't appear on any of there's a benchmark called I/O 500, which we should be on, but it's not possible to actually measure it on JASMIN, which is a bit of a pain. We also have 2 tape robots. If anybody's been to RAL, and you're quite welcome to, if you want to give me a shout afterwards, we can always give you a guided tour. We have these tape robots which have 10,000 slots apiece, and one of a brand new tape robot which JASMIN owns or paid for almost completely, which takes, each slot has a 7 terabyte tape in it, and then you think there's 30,000 slots in those robots. That's a capacity of about 10 petabytes usable. And then we have 12,000 cores compared to a supercomputer, which might be several hundred. But it's far more flexible. So we have cloud, data sharing, data transfer nodes, as well as being able to do batch computing, which is basically all a supercomputer actually does. So it's a complete environment. And with those component services, we can create workflows for all of the different projects, and all of their workflows are completely different. If you take a big supercomputer like the ones with the DOE in the States, guess what they get used for? They do lots of bomb simulations, and they run one program, and that's the thing that which the machine is optimised to run. JASMIN has 80 different projects on it, and every user, pretty much of all of the 2,000 users on the platform, has got their own code which works completely differently on the system. So it's a completely different ballgame from a standard supercomputer. So we have these huge range of workflows, and to support that, we have this network, which I'll show you a little bit later, which has a non-blocking bandwidth of about 12 terabits a second. We're not completely sure, but we think this is a fairly big chunk of BT's backbone network performance with low latency, and it's all Ethernet. So again, if you know anything about supercomputers, they all have a low latency network in the background, and it's run on something called InfiniBand, which has a latency between one computer and another inside the cluster of about 2 to 3 milliseconds. JASMIN can do about between 7 and 10 milliseconds, but they have a special network to do it. We just have the same kind of networking that comes in your broadband, but just much faster. And this is what it looks like. I'm not going to try to explain this. This is a diagram which our PI, Professor Brian Lawrence at Reading University, drew to try and get his head around about all the bits that we've got. But you can see it's pretty complicated, and that makes it good because we have lots of capability, but bad because it means that we have to train our users quite heavily in order to be able to make the full use of it, and I'll talk a little bit about that in a second. So we have a traditional batch cluster, if anybody knows about VMware. Sorry, not a batch cluster, we have a VMware cluster. We have traditional batch computing, so we have about 500 computers in this bit, and about 10,000 cores in this bit. We have different groups of storage with different types, which I'll talk about in a second. We have the tape library, and then the networking in the heart of it, and a bunch of networks, some of which have got dotted lines because they're outside of the site firewall, and some of which are inside JASMIN. So there's a constant tension between data coming in and out of the infrastructure and the data that's going around in here. We also have dedicated networks to the Met Office down at Exeter, to EPCC up at Edinburgh, that's where Arch is hosted, and also to Leeds University, which is a bit of a legacy thing. And then we also have links across the internet, obviously, to all of our colleagues in the other climate science programs, which I mentioned before. And this is kind of what you see when you log in. So a traditional supercomputer, you would log in on a command line. If anybody knows about SSH, you come in, you log into this node here, and that's pretty much where you stop. At that point, you might compile a program, submit it into the batch cluster, and then it will run, and you'll get your result, and that's the place that you'll take the data from. With JASMIN, this is just your jumping off point. JASMIN, you come in, this is just a bastion which takes you through the firewall and inside of JASMIN. You can log into a bunch of things in here. There's a bunch of transfer nodes which allow you to pull data or send data out or pull it back in again at high performance. And then we have a bunch of machines which are interactively, so you can just log into them and just start a program and it will start running. So we have a bunch of these things. They have a common software environment with some utilities which are managed by my colleagues at CEDA, and they're all common utilities for the file formats that we use. About 80% of the data on JASMIN is in a file format called NetCDF and HCF5, which I'll talk about a little bit more in a second. And so there are a bunch of utilities for reading and writing those kinds of files. A lot of it's Python. So from those you can run one job, and when you run out of that, which you can run 2 or 3 of them, you can only run them for about an hour before they get killed off. If you run out of that and you now want to analyse a whole data set, that goes into the batch cluster, and you could submit it from there as well. Then for some of our users, we have some cloud, what we call tenancies. So this is an interface where you can click a button, a virtual machine will power up. You can log into it through these routes through here, and those are dedicated resources just for you. They're not shared with everybody else. But we're actually moving more and more people to this model over here because with 2,000 users and half a dozen machines in the general usage pool, they quite often get completely swamped to the point where we've actually given up trying to manage them because it's too much effort. And then we have some external cloud tenancies. So so over here, these machines are interesting if you know anything about clouds. If you go to Amazon Web Services, you can pay with a credit card, spin up a virtual machine, you own it, you have administrative rights, it's entirely up to you what you do with it. That's this model over here, except they don't pay with a credit card, they just pay with, well, funny money. They don't pay with any money at the minute, but over here, this is more of a hybrid model. So they still have an interface to start the virtual machines, but when they pop up, they mount all of our storage over here, and we manage that. We have administrative rights on the boxes. They don't, but they can start and stop them, and they can do things with their users. They just can't install anything, and they can't do anything with the networking, which would otherwise completely mess this bit up here. But they can do anything they like over here, and then there's some sort of dotted line relationship to the storage. So this is where these virtual environments come out, which I'll talk about in a second. In a traditional supercomputer, you would have one big piece of storage which might be Lustre or GPFS, something called IBM Spectrum Scale. You might have anything up to between 5 and 10 petabytes of that for outputs from your supercomputer runs. In JASMIN, we have 4 different kinds of storage. We have something that we call parallel file system, which comes from our Parnassus, which is the thing that actually started me. That was the thing I was managing when I first came into JASMIN. We built from that small scale, we built 2 of the world's largest Parnassus clusters. They are at least 20 or 30% bigger than anybody had on the planet at the time. We've just decommissioned one of those, so we're now not record holders any longer, but hey ho. However, the thing that we replaced it with is this thing, which SOF stands for Scale Out File. It's a software-defined storage platform, and this comes from a company called Quobyte, and we have the world's largest installation of that by capacity. So it currently stores 30 petabytes of data. Then we have this thing, which is an object store, which I'll talk about a little bit later. That's from a company called Coringo, and we built the world's fastest object store from Coringo storage, and I'll talk about that in a second as well. And then finally, we have something that's based on solid-state storage, which is SSDs over here, and we use that mostly for doing compilations. If you're compiling code, you need to generate lots of little files really very quickly, and that's what this is good at, but these ones are less good at. And then obviously we've got tapes, then we've got the object stores, which I talked about, and then down here we have something which we call block storage. So in a traditional cloud, all of your storage is block storage. On your laptop, you have a disk drive, and the disk drive basically doesn't do anything until you format it. You create a file system on it. In a cloud, you're attaching that raw storage and then effectively formatting it to create a file system on top. And in a traditional cloud, that file system, you basically say, I want as much as I can get. And you'd think that would be a fantastic thing to do in an environment like JASMIN, just give me as much as I can have. The problem is that it costs money or complexity. So what we found is that this kind of storage is up to 10 times more expensive than this kind of storage here, and it's more complex, or it's more complex to manage. One of JASMIN's drivers is that we have a lot of capital money, so that's things to buy things with, but very little money to pay for people and support contracts. So everything about the procurement of JASMIN has always been around trying to get other people to do things for us outside of those environments. So we don't want systems that are cheap to run but take people to run it. Now we have other projects that are going on inside STFC which are funded the other way around. So they have loads of money to pay for people, but they have virtually no money to buy things with. So they're driven in a completely opposite direction. They can afford to have the complexity in having 3 people managing just their storage system, whereas actually even today, managing all of this storage, 44 petabytes is like 5 or 10% of one of me and the other 2 or 3 people in my team. Whereas other infrastructures have got teams of 10, 12 people effectively doing the same job. But they're just paid for differently. And so where we use that block storage, and we have about a petabyte of it, is for the virtual machines and the virtual research environments. This is the ELS Cloud, which is desktop as a service. These guys completely built their own environment, pulled in their own data. It's environmental genomics, so it doesn't really sit in the CEDAR archive. So these guys are running DNA analyses, looking for comparisons between the bugs that they're finding, trying to find out what bugs they've got from the DNA analysis. This is an ESA project, so this is looking at the data from the Antarctic I told about before. And the nice thing about these is that they can scale them up and down. So these guys ran training courses where they had 40 or 50 people in a room. We could scale up their resources, and when they'd finished with them, we could tear them back down again and reuse the resources. This is the same thing for this project, which was the OptiRad. They run a thing called Jupyter Notebooks, which are quite cool things, which they built an environment for themselves. And this is, we, as a systems team, we just provide them with the bare computing and the bare storage, and they build everything on top of that. And this is a bunch of examples of the other things that they've done. But this requires a lot of expertise to even to build these things, software expertise, and to run them and keep them running. And most of our users don't want that. They just said, give me a VM, virtual machine, to play with. So we built them a portal where they can literally just do that. And so many of our users are just coming in. This is a list of the tenancies. This is only a half a list of the tenancies we've got. This is different groups of users, and they can all come in, press the button from a list of templates that we give them, and then they can just power up a machine and do their stuff. But as I mentioned, when you're building a cloud, if you want to build a cloud where you just say, give me all the resources I want now, which is what happens with Amazon, they've effectively pre-provisioned massive amounts of effectively infinite compute and storage, and we can't do that. And the reason for that is because there's a tension with the batch computing. Lotus is our traditional supercomputer thing, so you submit a job into the batch cluster, and we have about somewhere between 6,000 and 10,000 cores running. This plot here is the pending queue, so this is the number of jobs that are waiting to run. You look down here, that spike is 1.2 million jobs on the pending queue. This is not unusual. We actually had a spike like this last week. Most of the spikes are more like this, which is 400, 500, 600,000 jobs. And you can see they're submitted to the queue, and then over a period of time the numbers drop off, which is about a day. Key thing about this is that before JASMIN started, that same kind of analysis, so that what they're doing is they're submitting one computing job for effectively every file in a data set, and they're grabbing a small amount of data from that, storing that piece of data. In the worst case, I saw somebody they wanted to do a statistical analysis across a data set of 400,000 files. So they put 400,000 jobs into the batch queue, retrieved one number, and then summarised up all 400,000. So that's not uncommon. Before JASMIN started, that kind of analysis used to take 6 months. With JASMIN, we went from 6 months to 3 days and now 3 hours for the same analysis. That was badged as groundbreaking. And as I'll say in a second, there are so many more things that people can do now which they couldn't do 8 years ago when JASMIN first started. So the critical thing with this is you can see, and this is just a zoom in on this part of the plot here. The blue line is the number of jobs that are waiting to run. The red line is the number of jobs that are actually running. So you can see actually this plot actually has the running jobs. but it's so small compared to these spikes you can't see it. The thing is, that's flat. So if I take a computer from the batch queue and I move it into the virtualization, the cloud, to give people more resources that are on demand, I have to take it away from this bit. And that means that these guys get impacted by doing that. So we're not the same as AWS, where we can just give people everything that they want now, but maybe they won't use it next week and it'll just sit there idling. We have to keep sweating the resources to get the most out of it. But this was the case up until 2018, and then those virtual environments, like the ones I showed you, couldn't really do very much processing. They could present websites with the data, they could share the data, but they couldn't actually do anything with it. Oh, sorry, they couldn't actually process their own data the same that we can in the batch cluster. And in 2018, we took the decision to increase it dramatically so that we can build environments for them where they can spin up the equivalent of our batch cluster and do their own thing. So you can see we effectively doubled the number of the amount of computing almost overnight. And that's targeted for cluster as a service, container as a service. So if people have heard of container computing, that's where we're doing it. The disk storage also got a similar kind of hit. This is the different kinds of storage. So you can see up until 2018, the blue bit is effectively our Panassa storage. As I say, we were hitting the world's top 10 for I/O performance, but it was all the same thing. So effectively, users never had to worry about where they were going. And then in 2018, we turned on another 3 or 4 different kinds of storage. But we needed to do that because the performance requirements were getting ever more, and the cost of these kinds of things were going up. If I say that the cost of this per terabyte at the time was about 3 and a bit times the cost per terabyte of this, so in other words, we can get 3 times the amount of this for the same cost as one of this. And the data that we're processing is huge. So this is a collective plot going back. This is back into 2015, but you can see these blue spikes here. This is over a petabyte of data being processed a day on the system. And as we add more storage, there are just more projects that are coming on and requiring more and more and more performance. And the only way that we can process that data is with a network. And when we started JASMIN, we had a little network like this. So this was 12 racks of kit. We had 4 network switches, about 40 ports on each one, I think, so 160 ports, and we went, yay, it's a great network. And we were really happy with it because it was super low latency and it did everything that we wanted. Interestingly, it was also from a British switch manufacturing company, which is, at the time, they actually went bust, unfortunately, but they were doing some really groundbreaking stuff. And this was another way in which JASMIN could actually help UK industry by working with UK companies. And then about a year, so remember JASMIN turned on in 2012. In 2013, they came back and said, oh, can we buy some more servers, please? And they went, yes, no problem, but we need some more network. So we had to completely change the network topology and add a couple of switches in here. This is all to keep the same performance going. And that was great for 2013. And then in 2014-15, they hit us with £8 million to spend, and it was never, ever going to work. So at that point, we took a step back to work out how we could build a network that would carry on forever going forwards, providing more and more bandwidth for more and more amounts of storage and more processing without ever having to do what we did here, which was to go from here to here and effectively to a different network, completely ripping it out and starting again from scratch. So we built this thing for the JASMIN 2-3 round in 2014-15. Even today, I think it's fairly unique to actually see one of these. Each one of these is a router. So this is the equivalent of your broadband router at home. It does the same function, but it's just much higher performance and much better. So what this thing here is doing is talking to 12 other things out on the equivalent out of the internet. Each one of these lines is a 40 gigabit, so that's 40, probably 400 times what your broadband connection is, and we have 12 coming out of each one of these. Each one of these switches here is talking to 24 servers with 20 gigabits on each server. If you add it up, that's just under a terabit a second of networking. Remember, I said that our 12 terabits a second is a significant fraction of BT's backbone network, and we're doing a terabit out of one rack with just 48 servers. We've got hundreds of these things. So we built this infrastructure here. These are all routers. We're managing about 6,000 IP addresses. So you remember on your broadband connection, you've got one IP address. That's the thing which is talking to the internet. We've got 6,000 we're trying to manage here. And this worked for a couple of years. As we added racks, this is the full thing. We started about here, and we started adding more of these things as we added more racks of kit in JASMIN 3. But eventually JASMIN 4 came along in 2018, and again, it didn't. Fortunately, we had planned this, but again, we had to do a change. So these kinds of networks, this is what I've just showed you, and this is another one, effectively upside down, placed on top of it, with a bunch of routers in here. JASMIN actually has 16 of these instead of 8 in the diagram, but these are the kind of networks that the likes of Facebook and Google and all of those big infrastructures actually have in their data centers. It's called a data center network because, surprisingly, it's in a data center. Many of the supercomputers don't have to do this because they're provisioned once and they're nowhere as big as JASMIN in its complexity. So we had to go to the kinds of architectures that Facebook use just to do JASMIN alone, and there aren't many of these infrastructures that look like this in the UK, certainly within the academic space, and probably not that many in the commercial space in the UK as well, because not many people have to get to this kind of scale. And so we connected JASMIN 2 and JASMIN 4 infrastructures together like this, and there's an interesting story which I won't talk about too much about. Even though we've got this massive amounts of bandwidth, it's still possible to swamp a network connection, and we had to do some very clever things to make sure that we didn't lose any network traffic going between any 2 points in the network, using something which again is unique probably in the world, the way in which we had to do it, but I won't talk about that too much. So, okay. So you'd be glad to know, we're on the last section now. Object stores. So an object store, all of our storage today just looks like your laptop computer at home. So you look at the files, you get the file browser up, there's directories and hierarchy, and you can go down you can click on a folder and it shows you some more files, you click on another folder, you go down. In the background, so the files all have, they're all part of one file system. But there is a new style of storage where instead of going down a file tree, you access each file with a URL. So just like in a web browser, you put in HTTPS and then you get to a web page, you can do the same thing with data as well. And each file has a unique URL. And that has a number of interesting advantages for us. We have a couple of projects. So I mentioned NetCDF and HDF5 format files earlier. They have an interesting property where the header of the file contains references to all the bits of data that are in the file. So if you're storing satellite data, you might store like several orbits worth of satellite imagery in one file. And each section of the file is like one picture. So if you store it if you imagine a file is a sequence of things all connected up, if you store them in the order that the satellite saw them, you get the first image, then the second image as the satellite moves around, and then another one, and another one, and another one. Which is fine if you just want to read out the data from the satellite in the order in which it was taken. But if you want all the images it took over the same place on the ground, you have to skip from the header to this place where it was over London, for example, and then you have to wait for another orbit, so that's further down the file, to pick out the next time it was over London, and then again and again and again. And what that produces in the file is a skipping pattern. So you read the header and you go, okay, I don't want all of that. It's like paging through a book. I don't need that. Oh yeah, that bit I need. Keep going, that bit I need. And that is absolutely terrible for file systems. They're usually set up, all those 220, 250 gigabyte a second numbers I talked about before are all based on the system streaming the data off of the file system. They're not designed to access it in this kind of random chunky way. Object stores can allow us to do that by breaking the file up into when you store a header and then you store those individual bits as individual objects. So you read the header and it says, I just want that bit over there. So that's what these slides are from my colleague Neil Massey at RAL. He's been working on this thing called S3NetCDF, and that is a Python library for chunking out these NetCDF HDF5 files into little bits. What he's reporting so far is actually the accesses are, unsurprisingly, a good deal faster than if you store the whole thing. If anybody knows anything about this, there's also the HDF group who actually manage the HDF5 standard, and they have a different way of doing it. So there's performance reasons for going to object stores, but there's also a bunch of other management reasons to do with the way which we grant users access, all the permissions that are on a standard file system. You know, if you've had a PC at home and you've got 2 logins on it, you know, files are owned by different users. Well, so imagine scaling it up to 2,000, 10,000 different users on the system, and we don't want them all accessing each other's files. With Object Store, we get rid of all of that problem. They can do their own authorization themselves. So we set off to buy one of these things, and so we were looking at how to run the proof of concept POC. So we looked through our file systems to look for what was the common size of file. And this is through these sort of several hundred million files. And we found that, roughly speaking, about 80 or 90% of the files were about 2 to 5 gigabytes in size each. And we went, great, okay, so we'll do the proof of concept with a 2 gigabyte file. But interestingly, object stores, which are mostly used in the commercial web space, they are only using 10 or 100 megabyte size files. So there's almost an order of magnitude difference between what we were using here and what the companies were actually using. To such an extent that one of the biggest companies, we managed to break their software right out of the box when we tried this proof of concept. The other part of the proof of concept was to prove object stores are usually seen as archive stores, so they're like the last tier of storage before you push the data onto tape, because they've been perceived as a slow archive thing. And what we were trying to prove here was whether you could make it go faster. Our parallel file systems can do about 75 megabytes a second per hard disk drive, per spindle. And then if you put thousands of those together, so here we are at about 8,000 disk drives, that's where your performance comes from. Each individual one isn't doing very much, but the more of them you add, the more performance you get. So we were looking for something that was about 75 megabytes per second per spindle, and I figured that if we could get 50 or 60, we'd be laughing. This would be fantastic. So I built a cluster which had about 2 petabytes of storage in it, and each server in the cluster, there were 13, had a 40 gigabit network connection. 27 disk drives in a box. This results from 2 different vendors. This is vendor A. We got 54 megabytes a second, and I didn't really do anything with it. We just installed it out of the box, and I went, "Whoa, that's pretty good." And then we did vendor B. We got 70 megabytes a second out of the box, again with very little tuning, and that was fantastic. Until I went back to the vendor, and we were comparing notes, and we realised that actually that was 40% better than they'd ever managed to achieve in their own labs with their own experts. And this is just done straight out of the box. And interestingly, the only difference between our proof of concept and their lab was the network. The network which I just talked about, the high performance, low latency network. And this one result here has turned into a bunch of white papers. This is a company called Coringo, and they have, off of that result and our installation of a thing that we bought from them, so we now have a 5 petabyte object store, which has 400 gigabit connected servers as the front end for that. This is characterising that system here. We wrote a white paper with them, and that has apparently opened so many doors to new business, because people never really realised that object stores could be used in this way. So this is another thing where Jasmin's kind of leading the world. So that's kind of mostly what I wanted to talk about. I'll just leave you with a couple of slides. So this is Jasmin user registrations. We've got a bunch of users here. This was just last month. 45 of our friendly users came to join us. We've done a few of these user workshops, big user workshops now. They've pretty much been sold out every time we've tried to run one. And that's a reflection of the interest in using Jasmin. Jasmin, I believe, is now researchers who are getting funding from NERC, I believe, now actually have to say how they're going to use Jasmin in their research when they apply for grants. But it's still, this curve here is the red one is the number of registered users from time zero, from 8 years ago. We're now over 2,000 users here. That is a very, very unusual curve for HPC systems. Normally what happens is you buy a big system for several £1 million. It's like Dirac, which I was talking about earlier in the IT Now. A bunch of users get on who are all the same kind of science. So like Dirac is all cosmological simulations. There tends to be tens to a few hundred of those researchers, and they've all got PhD students who are with them as well. So at time zero, they all register, and then a few of the PhD students go away, so the number of registered users drop off, more PhD students come back on again, so it goes back up again. So pretty much you get a spike, and then it's bumbling along the ground for however long the cluster or the piece of HPC actually lasts, and then it dies off the end when the funding runs out, which is usually after about 5 or 6 years. So Jasmin, as you can see, didn't do that. Jasmin started down here, and it's just gone dunk. Straight up. The number of user registrations per month, which is the blue line here, you can see has been going on up, where most months we're up at sort of 70, 80 new user registrations a month, and they don't go away again. This is just a reflection of the increasing number of projects and the increasing amounts of science that we're able to do as we add more capacity and more capability onto the platform. And this is just the number of registered users. That excludes all of the download users, which I talked about. There was a 55,000 number on an earlier slide. I don't really know what it is, but whatever it is, it's a lot of people around the world being supported by this platform. So we've got more people and more projects coming on, and that's being driven by more data. This is from one of our users, Mick Carter, down at the UK Met Office. This is a comparison about the amount of data that they have stored and other similar organisations have stored over time. It's obviously fairly blocky, but you can see this is an exponential number of terabytes stored. This is logarithmic. So here, 10 to the 3 is 10 petabytes. That's 100 petabytes. That's an exabyte. Down here, we're at 2019-20. This is just about where Jasmin is right now. So Jasmin's is between here and here, and you can see we're kind of keeping up with the data. But you can see by 2030, we're into the exabyte land. That is a lot of data. That's a lot of disk drives, and that's a lot of capacity. And the whole driver in what I've been talking about is to provide an infrastructure which allows our researchers to actually handle that amount of data at scale, at performance, and generate those results that we need for the next decade of climate science. Without systems like this, things like the IPCC Climate Change Report would just be guesses about what we're going to do, but they're now becoming ever more accurate. And hopefully you can see from what I've talked about that systems like this are a necessary part of that research. So thank you very much for listening. Questions, if you have any?
Jonathan, with today's technology, will you be able to scale to meet what you need in 2030?
Yes. Cautious, yes. About a year or two ago, it was looking a bit shaky. The disk drives that we use in JASMIN today are, and I use disk drives, everybody talks about solid state storage. There is no way that the cost is ever going to come down. Everybody talks about, oh, it's all going. But at these kind of scales, it's still disk drives, and it probably will be forevermore, disk drives and tape. About 2 years ago, there was a transition in the disk drive market, and we went to the, first of all, the helium drives, which is an utter waste of helium, if anybody knows anything about the helium market. They put helium inside the drive so that the drive heads could ride just microns above the surface of the disk drive. And that was pushing the technology to its very limit. And then there was, very recently, there's been a transition. We're now going into the drives that have vertical encoding inside the drives, which has just been coming on stream. Everybody wasn't sure that the vendors would be able to do it, and now it looks like eventually they are actually capable of doing it. So now the disk drive densities are now starting to scale back up again, and the vendors have got plans to go to 50 and 100 terabyte disk drives. You know, if you think on your laptop, at best you might have a terabyte drive, think about 100 times that in the same scale. So if you scale it up, the same number of disk drives, you're scaling up by a factor of 10, and that will get you to the exabyte region with more racks and more kit. So it is possible, but it is a big effort. Yes?
When are you going to invite Donald Trump to come over and have a look at the work you're doing and show him that it's not fake news?
Yes, well, quite, yeah, right.
Jolly well ought to.
Yeah. Yes, that's a hard one, but anyway.
Does this data hang around? I mean, how long can it take to get?
Yeah, good question. The problem with environmental data is you can't ever recreate it when you measure it. Obviously, if you run theoretically, if you run a simulation, you could rerun it to get the data back out. But the Hermit example I used earlier, that was a whole run on one machine for 1 week. You don't get very many opportunities to do that, and that's why you don't want to throw the data away afterwards. And it's the same when you're actually measuring the data. You're never going to be able to measure that Icelandic volcano again. The data is the data. Every earthquake is different, every landslip is different.
So you need to keep data for years and years?
Yep.
How do you do that?
Essentially by pushing it to tape.
How long do tapes last?
If you look at what's happened with the CEDA, the slide I showed earlier were the 20-year history of the data sets. Obviously, the tapes that we're using today and the disk drives are not the same ones that they first stored the data on 20 years ago, but the data is still there. I don't know if anybody's old enough to remember the laser disk drive Millennium project that the BBC had. Do you remember that one? Yeah. And there was this story when they came to actually read it back in, I think it was 2000, wasn't it? They didn't actually have a reader for it any longer. So part of the reason we actually have CEDA is they are data curators. And one of their jobs is to keep moving the data forward in time as we go forward onto different media and making sure that we didn't corrupt the data when we moved it from one set to another. And it turns out that's a lot harder job than you would actually think. As an example of data migration, it took to get the data onto JASMIN from where it was, they had about a petabyte of data pre-JASMIN on about 120 NFS servers. It took me about 6 months to move the data of petabyte. Remember I said you can move a petabyte in a day? It took me 6 months to move the data off of the old disks and onto the new one, and it took another month or so to actually crunch through every data signature on every one of those files to make sure that they come across, and some of them didn't come across properly. So you have that every time you do a data migration. The same thing happens with tape migration as we're moving forward in generations of tape. So it's a big problem, and that's why a lot of the things like the climate research programs they have, and also the particle physics programs, if anybody knows anything about CERN, the LHC, they have data centres scattered across the world. So if something went horribly wrong and you lose a whole data centre, you don't lose all the data because you've got other copies at other places in the world. That's not necessarily true for JASMIN data, and so we don't back it up, but there are ways in which we can get some of it back in. That's a good question.
Are you running out of physics at RAL?
Yes and no. We, on our JASMIN, the end of JASMIN 5, which was last year, we used up the last available rack in our current data centre, apart from some special ones I won't talk about. And that's the reason, if you remember on the first slide, I had the 2 red arrows to the 2 data centres, and that's because we've refurbished. There's a building called the Atlas Centre at RAL. It's called Atlas because it used to hold an Atlas computer from the 1950s, I believe. We're using the same data centre, we're using the same room. Obviously it's been completely refurbished where the Atlas machine used to sit. But in order to stitch in storage, which we'll eventually have over there, and we will need that for the exabyte kind of thing, we'll need those number of racks. We've built a very high capacity pipeline between the 2 data centres, which is far more than, I think it's about 400, it's capable of 100 times 400, whatever that is, like 400 terabits a second or something like that. It's an unimaginable, at the minute, it's an unimaginable large value. So we have plans to be able to do that, but it very much relies on technology moving forward, so that we've got, so those disk drives keep getting more and more data on them, and us to keep migrating the data, as I've talked about CEDA having to do, to keep the same data on fewer and fewer disk drives. We've already been through with JASMIN, when we first started we used 3 terabyte drives, and we're now on 12 terabyte drives. So in the space of 8 years we've compressed with the same amount of data, takes up a quarter of the space that it did in 8 years. So as long as that scaling keeps going, which it looks like it will do now, will be good to keep an exabyte of data in the space that we've got. Managing that data is a different matter entirely. When you've got literally billions of files, that's not an easy thing to make sure they're all there. Yeah.
I hate to lower the tone, but what impact is Brexit having on your work?
At the minute, had I not been doing this talk today, I would have been on the phone trying to get some purchase orders out to beat the deadline. We're trying to spend a number of £1 million this year, which the Research Council only told us about 6 weeks ago. If only we'd known. And the reason we didn't expect to be having any funding this year was because of Brexit. So we knew that money would be tight this year. So it was in the plan, which we gave to the Research Council, but there was they eventually decided that they were going to give it to us, but it was a bit later in the year. Normally we'd have known about this back in April, May time, where we'd have had lots of procurement lead time. Now we're getting into the back end of the 31st, and the problem is, the only real problem for us Brexit-wise is that the dollar-pound exchange rate is completely unknown beyond the 31st of October. So as long as I get my purchase orders in before the 31st of October, everybody's happy because they've all hedged all of their dollar-pounds, and obviously all the stuff that we buy kit is in dollars, so that's important for us. So I think we can do that. The other impact, of course, is European collaborations, and the government are committed to. There's the Horizon 2020 programs, which I don't know if anybody's heard of those, big European science funding. STFC, and specifically the Scientific Computing Department, where I come from, has collaborated with lots of people around Europe on those programs. The government committed to backfilling any resources that we lost if we left and we weren't able to work with 2020 programs any longer. But, who knows what will happen with that? So those are the things. But obviously we have international collaborations, and most of those international collaborations are virtual rather than moving people around the world. So things about visas and all of that kind of stuff doesn't really impact us too much. So it is an impact, but we're sort of managing it as best we can.
What other similar scale environments exist like JASMIN elsewhere?
So JASMIN was, we went to the IEEE Big Data Conference in 2013, I think it was, and I stood up and made a presentation about JASMIN, talking about how we were using disk drives, and everybody looked at us completely strange and they went, what the hell are they doing? I didn't see any presentations about that looked anything like JASMIN at the time. 5 years have rolled on, and now people are trying to. I would like to say people have seen the light, but there's a different way of doing things. Horses for courses. So there are certainly in the UK there are 2 or 3 infrastructures that are similar to the. So the Crick Institute built something that was similar to JASMIN. The Met Office have their own system that's a little bit like JASMIN. There are a number of people around the world who've sort of got systems that sort of have mixed clouds and parallel storage. Most of them tend to be related, associated with supercomputing centres. So, for example, the Australian National Supercomputing Centre has an infrastructure that looks a bit like JASMIN, but they actually do have a supercomputer as well as some other bits and pieces as well. So but they're a bit more focused than JASMIN. We're a bit more general purpose. So they are scattered around the world. There's a couple of we've been talking to POX, I can't remember now. NCAR in the US. So they're the climate and weather forecasting people. They're trying to build something that's a bit similar to JASMIN. So they're definitely around. It's kind of the story I was trying to tell when I started about my boss coming to me and said, we all went, well, yeah, we can do that. But to us, it was sort of obvious that that's what was needed. But to the scientists where they were coming from, it wasn't at all obvious that those are the kind of things. So putting together what we saw as fairly standard pieces of IT and capability at the time turned into something that was groundbreaking for them. But batch clusters were kind of our bread and butter. So from my perspective, it doesn't look like it's something new, but from those communities, it looked like it was something that was very new at the time. So,
You say you don't do any backups. Could you just not duplicate the tapes that go into your archives?
Yeah, we do. I think what I meant by we don't do any backups is we don't do any disaster recovery. Well, it's not quite true, but we don't do any disaster recovery backups. So when I said we have 100 petabytes of tape capacity, actually what we have is more like 300 petabytes of tapes. So many of the data sets they're written to 2 tapes, and the golden data sets are written. Well, actually, the golden data sets are written to 3, and then there's another off-site one. So for the ones where SIA is the golden data set holder, the last resort, we have off-site backups. Actually, we share tapes with Column as well.
So that gives you some disaster recovery.
Yeah. So for the data that SIA have been mandated to actually hold, it's not going to go away. So if an aeroplane lands on rail, we'll be able to get the data back. For data that's more ephemeral, so things where scientists have gone out into the field and they've measured some data and they bring it into JASMIN, obviously they don't tend to delete it back at site, but the copy that's in JASMIN is the copy that's being used to do data into comparisons and model into comparisons. So usually they have a copy as well. It would be a bit rash and they are actually told that there is no backup on JASMIN because physically we couldn't do it. The tape that we have isn't really we have this system which I didn't talk about called elastic tape, and users get an allocation of disk and they get an allocation of tape, where usually the tape is about twice the size of the disk, and that's because even with the data sets they're doing, it's a bit difficult to actually, if you're given several hundred terabytes of total capacity, it's unrealistic to expect you to be able to process all of that just like that. So you don't need it all on disk. And so the reason for the tape is to be able to effectively shuffle it backwards and forwards between disk and tape. So that today I'm processing this bit, and then tomorrow I'll be processing this bit that's on tape. So I've kind of forgotten what the question was now. But the backup. So we do have backup, we do have tape, but it's not primarily used for backup unless it's for the golden data sets, where we have 2 or 3 copies. And that's the stuff in the archive where the data's been given to us to manage it. When the users are finished with it and we get it in the archive, we maintain it. Until that point, it's their data, and the fact that they're bringing it to JASMIN is just so that they can share the data more easily with other people, or they can process it faster. But the expectation is that it's your data, you've got another copy somewhere else. So if anything goes wrong, you can always pull it back again.
Excuse me, do you think it's possible to collect, for the supercomputer, to collect data from the Arecibo observatory, or like the 500 meters apparatus, like the radio telescope? Is it possible to collect the data from?
It is. So we have, as an example, STFC funds. The square kilometre array and the square kilometre array. So if anybody knows, if you're aware of the square kilometre array, it's a huge effort to produce an antenna that has a square kilometre but it has an aperture that's the width of the planet. So part of it's in the desert in South Africa, and another part is right in the heart of Australia, about as far away from radio interference as you can get. The data that thing's going to generate is more than the 10 terabytes of data that we're talking about from space with Sentinel. We're talking about petabytes of data, an order of magnitude up from what the LHC generates for their particle physics data. So there are massive programs going on right now to design systems to pull data from the telescope heads back to places like JASMIN, but not JASMIN itself, but in similar kinds of data centres. So the UK arm of that is funded by STFC. There's some work that's going on that's funded by STFC and inside our own organisations about how you would actually do that, how you would build the networks and the computing and the storage to cope with that. There was anybody saw the story about taking the image of the black hole? Have everybody seen that one?
Yeah.
It's a really nice story. There was a BBC programme about it I watched a few weeks ago, and they actually had, I don't know if anybody watched that, they had racks and racks, they had boxes full of disk drives. You see those? And they actually, they showed the thing where they were actually taking they'd written all they had a similar thing where the antennas are effectively scattered across the world, and they need to bring all the data to one place to do the analysis, a bit like you do with JASMIN for environmental data. And the way that they transmitted the data was by taking the disk drives, putting it in a box, and then sending it FedEx to the which is a very high latency, high bandwidth route for transmitting data. The reason they hadn't built a network infrastructure like the Square Kilometre Array is doing is simply because it was a one-off thing. Square Kilometre Array is building national data transmitting infrastructure to be able to stream the data off the telescope, because obviously it'll be running 24 hours a day, and the data will be coming 24 hours a day, just like it effectively does for the particle physics data as well. So, there's learning that's going on from what the particle physicists have been doing with the LHC and their data streams, which is going into things like the Square Kilometre Array, and it's just data a bit like Arecibo is. and so there's learning from particle physics, there's learning from architectures that are a bit more like JASMIN about how you build systems like this. Strictly speaking, we could take data from Arecibo, but it's not what we're funded to do. That's astronomy, cosmology work, and JASMIN was built specifically for environmental scientists. If you stop me doing my job and you ask me to build something that looked like JASMIN for the cosmologists, I could probably do that. But it would be, as you can see from this, we are, actually from this plot here, we have the capacity to hold the data, but the big data stores in JASMIN have only been available for use in the last 18 months, and we are already 44% full within 18 months, and that's on a 44 petabyte infrastructure. So in another year, we'll run out of disk space, and probably tape space as well. So basically, there's no room for all those cosmology people. We don't want to talk to them. So.
What are you actually doing about maintaining your staff capabilities? You said that you didn't have enough money to operate them.
Yeah. We just treat them very well. We feed them donuts.
Turn over a training program trying to keep the information up.
Yeah, no, it's a very serious problem because clearly with a small number of staff, one of them goes, and if you're not careful, all of that information just walks out the door. So there's two things that I've been doing which are to try and avoid that. One is by making sure that everything that we do is documented. It's not in somebody's head. So we have huge wikis with all of the information on it, and it's in a lot of detail as well. So documentation is key. The other one is more of a kind of a long-term, and we're trying to. There's myself now, and there are 3 others in my team. One of whom has only just joined in the last couple of months, so effectively 3 people. We try to make sure with those people that everybody is a generalist, so they all know everything about everything to some extent, and that, so when they actually start reading the documentation, they know what it means. So if somebody is not available, or more likely is away on holiday, we can cope with anything that goes wrong. So that's one thing. But the other thing that we're doing is, because of that problem, and that happens a lot in open source projects. So I mentioned my colleagues who are more funded for recurrent than they are for people than they are. So if those people then disappear, obviously they're taking a lot of knowledge with them. You will notice that I pretty much didn't mention any open source project names when I mentioned any of the storage that we were using before. So the word Ceph didn't come up, for example, actually for good reasons, but technical reasons. Ceph is an open source storage thing which does block storage and to some extent file storage. So a lot of our other infrastructures which are hosted by STD, they use that kind of storage. But it requires a team of people who are dedicated to running that, and if they disappear or they're sick or they get run over by a bus, all the knowledge effectively disappears with them. We get around that by buying commercial systems, so that works for our capital, and that means if anything goes wrong, we just log a ticket with the vendor. Or actually, even better, in most of these systems, they've been procured in a way in which the vendor effectively manages the storage for us. So it's effectively like getting rid of the problem by giving it to them. So with all of the pretty much, that's not quite true, but with most of the storage, the only time we ever touch it, the vendor's monitoring it for us, either the supplier or the end technology vendor. They're doing all the monitoring remotely. They detect the error conditions, and the only time we ever hear about it is when they send us an email that says, please change drive 3 in server 10. And that's it. And then we have a bunch of spares. We just go down to the machine room, change out the drive, and that's the only time we ever see it. That's the theory, and most of the time it works. And obviously you get into users do weird things with the storage, and there's a bit more interaction going on with the suppliers. But most of the time we're just saying, hey, there's a problem, deal with it, and then we don't have to worry about it. So that's where we're using a lot of commercial systems, whereas other infrastructures are using more open source things. Now, very interestingly, people have criticised the way that Jasmine's been built like that. They go, oh my God, you're spending all this money. Well, it's the only money we've got. You know, you gave us capital resources, that's all we can spend. But the other thing about that is now we've had time with Jasmine to actually compare the costs of running with small people, big capital, where you offload all of that knowledge effectively to the vendors, versus the big people, small capital, and guess what? Over 5 years, they're about the same. So, you know, it depends which model you want to go with. Yeah.
What is the software you use for, or what does it look like for the core allocation to keep all your customers, like when the demand fluctuates? What does your system look like?
So far, we've been lucky. The only thing that we've actually had to quote it is storage. So you saw that those spikes of computing were actually quite small, and so they only last a day or so. So most of the time, you saw that the spikes weren't overlapping on the pending queues, and so we haven't had to quota it. We are talking about doing quotering, but so far we've managed to provision more compute before people actually have to worry about it. So it's not an issue that we've had to get involved in at the minute.
In view of the time, unfortunately, I'm going to have to draw this to a close.
Sure.
So I don't know if there's one final question anybody wants to. It's burning to ask.
Why the name Jasmine?
Oh, yeah. Okay, so I had a slide on that because I thought somebody would ask this. It's an acronym, obviously. It's not Jasmine, the name of the person with an E on the end, which people obviously get confused. It stands for Joint Analysis System Meeting Infrastructure Needs, which you can tell is a gobbledygook made-up thing. So the joint, because it's jointly delivered between STFC, CEDA, funded by NERC, and the users. A is for analysis, which we've kind of talked about. System it's a system, surprisingly, and the min on the end was basically meeting a bunch of needs from all of the people who I talked about the way in which people were doing analysis before Jasmine came along, and it was effectively meeting their infrastructure needs to do this kind of big data for environmental. So that's where the name came from, but I think Brian invented it because he was into tea ceremonies or something, which is why it's called Lotus and Jasmine, right? So.
Well, I'd just like to thank Jonathan for a fascinating talk and giving us some insight into stories that we probably don't come across in our normal lives. So thank you very much.
Thank you.